All right,
All
you
right.
are good to go.
All right. Thank you, Steve. Okay. So welcome to this today's session of Ask an Expert. This one will be on time enclosure. We've had this session a couple of times in the past. It's been a while, so we are bringing the session in again. I will be your expert on time enclosure issues, and so my name is Stephen Elzinga. Welcome to the session. I've been in the FPGA business for my entire career. More recently, joined the training team here at Intel. It's been about 5 years now, and been been enjoying it ever since. I in the past I was a design engineer and also an application engineer. Again, just doing all things FPGAs. I think the technology is great. I've taught a wide variety of classes. So more recently, my focus is a little bit more on timing and time enclosure related issues. So access to resources, you go to our webpage, Intel homepage there. You can go ahead and click on those different resources. A lot of the resources do require an Intel account, so be sure to sign up for an Intel account. Once you sign up for the Intel account, you have access to sign up for classes that we have. Currently, our classes are being offered for free, instructor-led. So check out the schedule, see if there's an upcoming class that interests you. Let's see, different resources and information and documentation available on our websites there. We also have a YouTube channel where we highlight a number of our online trainings on YouTube. And in addition to online trainings, we have something called a quick video. Quick video tackles it introduces a topic that's around 5 minutes, a topic that can be succinctly described in 5 minutes. We have those quick videos. We have hundreds of videos on those, so we have a lot of content on YouTube to look at as well, to learn more about Intel FPGAs. Okay, so the ground rules. So any questions you can think about time enclosure is good. Just ask away. For that matter, I'm game to indulge any questions FPGA related. If I feel like it's getting a little bit too far off topic, I'll let you know. I'll give you my best answer, and based off my experience, if I don't know the answer 100%, what I'll do is I'll jot it down and follow up with that. We may also refer you if the question gets a little bit too involved, too design specific, we may refer you to your local FE. So be aware of that also. But anyway, since this is an Ask an Expert session, we do hope to be able to answer the questions as completely as we possibly can. So Steve Strell, yeah, go ahead, Steve.
Hi. So just following up on Steve, I am the other Steve S. I am your moderator today. There are two ways that you can ask your question, whichever you are most comfortable with. If you want to ask by voice, you can unmute yourself. Feel free to ask and interrupt at any time. And Steve will be able to acknowledge you, or you can enter a question in the chat. I will be actively monitoring the chat all the way through, and I will be relaying the questions that you ask, as well as questions that we have received ahead of the class to Steve. So I think without further ado, Steve, I think that you're good to go.
Great, thank you. Okay, so while you're here, time enclosure, don't I just buy a faster part? It's like, well, if we all had infinite budgets like that, I'm sure that'd be the easier way to go. Doing time enclosure with the chip planners, like squeezing a balloon. And so yes, if you find yourself working in chip planner a little bit too much, then it's time to figure out some other time enclosure methodologies. Chip planner is an excellent tool, but it's not the save all for time enclosure issues. I know Intel has some of the fastest FPGAs, but I need them to go faster. So that's the idea here. Hopefully we discuss and talk a little bit about techniques to be able to help you achieve that goal there. Design Assistant does time enclosure too. Yes, so Design Assistant is a nice handy tool inside of Quartus that alerts you to potential time enclosure issues. So if you're not too familiar with Design Assistant, check that out. It has a lot of nice reports in regards to that. I'm just stuck. It's like, yeah, sometimes you're stuck. You just don't know where to go. And so hopefully we can give you some ideas on what to do with that as well. So about time enclosure, time enclosure can be frustrating. You go through your design, you think you've done everything properly, and you end up with timing errors, and you're not exactly sure where to turn, what reports to look at, how to make sense of the reports that we have. Do you have to go and go back to the drawing board with your design? So these are all issues surrounding time enclosure. And so there's not a one solution that fits all scenario. There's hopefully the idea here is to be educated what's available to you in the software tools, and then once you understand and appreciate what's available to you in the software tools, hopefully that'll come to mind when you come across a particular issue, what part of the tool set you need to use to help with time enclosure. So one of the things I want to talk about this time, and there's always a little bit of content to kind of get people thinking about it. Last time in closure session I did, I think I talked a little bit about design assistant, so to get people a little bit familiar with that. This time I decided to talk about the concept of seeds, and it's mixed when I teach classes. Some people are familiar with seeds, other people are not. But with the concept of a seed, and so a seed is something that starts a process off. For example, it's people might be familiar. If you want to start a random number generator, you have a seed number to start with, and the random number generator goes from there. So likewise with Quartus, not saying that Quartus's place route process is random. It definitely is not. But if you consider the potential solution space that Quartus has to finding a solution to the problem being your design, there's a lot. And so just as an example that we have here, you consider a Stratix 4 part. If you have a design that's one register, so you have over 180,000 possible locations. So you say to yourselves like, well, Steve, that's a trivial design, and yeah, and probably every single one of those locations would probably be just as good as the other. So there's really no problem with that. 2 register design, you can see it's like, okay, so the locations, the potential locations, starts becoming very exponential quickly. So 2 register design, 33 billion solutions. Again, 2 register design, trivial. One solution is probably going to be just as good as the next. But as you kind of see where I'm going here. 3 register design, the whole idea here just quickly balloons. And with the 16 register design, there's more solutions for a 16 register, more potential solutions for a 16 register design than there are atoms in the known universe. And so we have this. So Quartus has this problem of being able to find a solution to the design space. And so designs are going to be a lot larger, infinitely larger than 16 registers. And so this whole, again, kind of going back on this concept of seeds, Quartus needs to know where to start finding a solution to the problem there. Now, between runs, there could be potential where Quartus picks a different location to start the place and route process. Okay, that's part of the variance that we have here, and typically what you probably will see if you do some seeds, and again I'll talk a little bit more about the concept of seeds. There could be a plus or 5% variance between these different runs, and that's a normal part of the process. It's normal part of the time enclosure process, and so to illustrate this point, people are frustrated at times, not everybody, but people are frustrated at times like, well, I made this small change to my HDL code and now I can't close timing. So part of how Quartus understands, or part of how Quartus determines where to start finding a solution for this place and route process is based off of, and I'm going to say an internal seed number. So this internal seed number gets generated by the inputs that you have in your design. So if you have all the same inputs in your design, you're going to get the same outputs. That's why I said Quartus isn't random that way. But if you vary the inputs at all, then that varies this initial internal seed number that Quartus has to start looking for a place and route process. So the inputs can be, or the inputs are, let me say this, are design files, so source files, so Verilog, HDL files, memory initialization files, synopsis design constraint files, the QSF is the Quartus settings file. So if you change a setting inside there, that's going to tweak this internal seed number ever so slightly to choose a slightly different solution to the problem that you have here. The version of Quartus, what operating system you're running on, Windows versus Linux. So all these play a part into determining this initial internal seed number that Quartus has to start the placement of process. And so that explains, even though it explains, it doesn't take the pain away of, well, I just made a small change in my design. Now it doesn't close timing. But that's what's going on. So it's not it's not a bug of the tool. It's a feature. It was made that way. Quartus has to do something like that. So the summation of all of these, inputs at compile time is a seed. And again, I'm going to call it the internal seed number. Changing any one of those will give you different results. So just be aware of that. But there is this idea of what we call seed sweeping. So seed sweeping, what you can do is, and by and large, there's going to be some caveats. I'll talk a little bit about the caveats later. But by and large, if you are done with your design and you want to eke out some more performance, or if you think it's like, what, I am so close to closing timing on my design, everything is done, I'm, a couple of percentage points away. And if you're that close, you can do what's called a seed sweep. And so what you could do is there's still a way to tweak this internal seed number by setting up an external seed number. And that's why I said we're going to call it an internal seed number, because there are two differences. So we call this in the fitter settings a seed number as well. So here we see the fitter initial placement seed. It's by default 1. One seed number isn't a magical number over another seed number. A seed number is good for your particular design scenario at that current moment in time. If everything is frozen and you find a good seed number, that is the seed number that will be good with how your design currently exists. And so the idea with the seed sweep is that you go through and you change this number. You can change this number however many times you want to do the variance. And remember, I talked about the variance is going to be plus or minus 5% variance potentially on average from compile to compile. So what you want to do is, by doing a seed sweep, you go through and you try some of these external seed numbers to see if you can get just that much more performance out of your design. Now, people will say that this is a last resort thing to do, and last resort kind of has negative connotations, and it's definitely, there's nothing negative about this. It's just the last, you want to do this as the last thing because it doesn't make sense to do it prior to that. Again, there's a caveat with that. I'll explain that in a little bit. If you do it prior to that, you're potentially wasting your time. So you don't want to do all these compilations when your design is just not done yet. Okay. So talk about seed sweep, talk about it's a last resort performance gain, because that's just where it makes sense to do it, is that when your design is done. So with the seed sweep, you can go ahead and monitor the changes, see what seed value gives you the best performance, and see if you can get past that hump that you're trying to get to in the timing closure process. Let's see here. Okay, so why run a seed sweep? So here we have an examples number of seeds. Here we have start out the default seed number, and this is just an example for purposes of presentation. Let's say your base frequency at seed 1 was 604 megahertz, and doing a seed sweep here resulted in a number of different megahertz, a number of different Fmaxes, all of them better than 604. Best one in this example that we have here turned out to be seed number 4 is 642. So this is why you'd want to do a seed sweep, to get that performance that you're looking for. Now, a nice way to do a seed sweep automatically, I'm not going to talk in detail about it right now, but I definitely can if there's interest, is running a tool called Design Space Explorer. And Design Space Explorer, what that tool does is it takes command of your Quartus project. In fact, it asks you, like, oh, your Quartus project is open, you want to close it? You say yes. And what you do is you're able to explore your design space. So in other words, all those settings, or there's a lot of settings that you can have a Design Space Explorer go through. A lot of the fitter settings, for example, the placement effort level. And in addition to those settings, you can have it do a seed sweep. So go through all those different compiler settings as a single compilation point, and after going through all those different compilation points, it will then iterate on a new seed. And so as you can see here, the number of compilations um, will expand very quickly. But what you're doing there is you're trying to get that last bit of performance out of your design. And so that's again, that's what the Design Space Explorer. If you're comfortable using the tools in command line, doing a seed sweep command line is really straightforward too. And I don't go over that in these slides, but just be aware of that. If you're comfortable on the command line, setting that seed number option to iterate through a loop is relatively straightforward to do. So here's a graph that I got recently from one of my colleagues, and these were done on internal designs on various different seed sweeps. And one of the benefits of doing a seed sweep and running Design Space Explorer is Design Space Explorer can actually farm out your jobs to different computers located on the networks. Now the computers have to be set up to be able to accept jobs and stuff like that, so you're not stuck with just staying on your local computer to have your local computer be bogged down. You can farm the job out to a number of computers. So with this graph, what this graph has shown, we see on the bottom here number of seeds that were run, and then we see the Fmax. So we start off at just one. It's not 1 megahertz, but 1 is being the baseline, and we see this as a percentage of increasing. So here we see high effort. The SE stands for superior effort. And so these are different settings that were used inside of Quartus itself. And we see that with the number of seeds being swept, we see that there was each data point here is the average highest maximum Fmax that we're able to get. So in other words, if we did if on average seed sweep running at about 5 seeds gave you on average 4% improvement in your Fmax. So that's what these points are showing here. So we can see that the real benefit, if you don't have the time and resources allocated, the real benefit is doing a seed sweep of about 5 seeds. You can see a sharp improvement there. We do see more improvement, not as much as the first 5 seeds, but more improvement after an additional 5 seeds, so up to about 10 or 11 seeds. And we still see improvements going on. But if you have the time to run 41 seeds, we can see that you can get as much as going from your base Fmax up to about 6% improvement by doing a seed sweep. And again, seed sweep you could farm out to multiple computers on your network to have them do that job. So if you do have the time and the resources available, it might be to your benefit to try out seed sweep. Okay, so now I mentioned before that usually doing a seed sweep is a last resort thing because that's where it makes sense to do it. Your design is done. You're not contributing to this internal seed number anymore by changing the source files. But I said there's a caveat. And the caveat here is that you could do if you have a fair number of RAM and DSP blocks in your design, what you could do is run your design and run a seed sweep on your design, even though it's not completed yet, and find where you get a good Fmax for your design placement or the placement of the DSP and RAM blocks. And what you do at that point is after you've done a seed sweep, you found a good Fmax, you can go ahead and back annotate the placements of the DSP and RAM blocks. And to do this, what you do is you go inside of Quartus, you go to the assignments pull down menu, back annotate assignments, then you go ahead and select the RAM and DSP assignments there. It'll back annotate that. So basically what you're doing is you're assigning locations to those RAM and DSP blocks. And so the fitter has found a good placement for those after you've done a seed sweep. You say, like, you know what, I like those. I don't have to do the seed sweep every time. I want to assign those locations now. And that's the idea with the back annotation right there and doing the seed sweep. And again, on an internal design, by doing this process there, we have a base Fmax listed here. They did a seed sweep. And again, this was a design that had a fair number of RAM and DSP blocks. They found that seed 6 was good in this case. And so they back annotated the location assignments of those RAM and DSP blocks. Then as the design matured, they were able to have a design that produced not as much variance between seed sweeps, but they already started out at a good placement for those. And so after the back annotation was done, the design matured, and here we have the F maxes on the various seeds here as well. Now, when I say that there's less variance, we see that the spread of the frequency of the megahertz between designs is only 26 here, whereas previously it was 87, and the seed value here was about 460, which was right at the average that they had for the seed sweep. And so again, this is back annotation of your RAM and DSP blocks doing a seed sweep on your design. This was before your design was completed. So that's why I said there's a caveat there that doing a seed sweep is last resort. If you're not back annotating placements of your RAM and DSP blocks, then yeah, doing a seed sweep makes sense when your design is complete or nearly complete. So that was my little introduction of seed sweeps. Anyway, I'm open for questions here.
All right. So somebody did ask about how to do a seed sweep, and I know you mentioned it. Maybe you want to show the the Design Space Explorer very briefly.
Yes. Let me see
if you can bring that up.
Yep. Let me do that. The design that I've got, hopefully, will be responsive. The design I've got is pretty substantial. But let's see here. So tools. Design Space Explorer. So you'll see that, we'll see how long this takes. This is okay. So that's why it says, Design Space Explorer will kind of take over your Quartus project. So you get this prompt here saying close Quartus Prime software and open the project in Design Space Explorer. I'll say yes. So wait a minute. This design that I had loaded up was quite large. It filled up almost an entire strat extend part. So you don't want to save changes. No.
I could give you a question while we're waiting.
Yeah, go ahead. Thanks, Steve.
All right. Let's see. Over constraining. So there is a question that we got ahead of class time about over constraining, that it's worked in the past. I was going to try it in my current project, but it's no longer recommended. Why is it no longer recommended? What's wrong with over constraining when I know that it did work for me in the past?
So that's a good question. That comes up, and I actually have that in my timing closure class that I deliver. And see, I've got those slides up. Give me a moment here. I can chat a little bit about that. Let's see. Okay. Let's do this. Let's hopefully I can. It is. There we go. Okay, so over constraining. So I don't know what the idea of over constraining became not recommended, and maybe it's just a wrong idea about over constraining in general. So you can look at it. You can look at over constraining in a couple of different ways. By over constraining, what you're doing is you're changing the SDC file, right? So that tweaks the internal seed number that Quartus uses, so potentially finding a different solution. So there's that involved. Also, what you're doing by over constraining is that you are telling the tools that, hey, this path, I want this path to have a little bit higher priority than the other clock constraints. Let's see here. That's input delay. Okay, so let's talk about this. So set max delay. Set max delay is a timing exception, and it's a timing exception in that it overrides what your general clock domain constraint is with the create clock constraint. So you do a set max delay, it overrides the clock constraint, and because it overrides, it has a slightly higher priority than the create clock constraint. And what you're doing at that point is you're constraining that particular path, which will have precedence inside the tools. And so there's a good chance that you'll be able to. Well, it has a higher priority. There's a chance that you'll be able to get that path to pass timing. So there's always going to be a trade-off. So if you get a path to pass timing, that means something else had to be rejiggered or accounted for elsewhere in the design. So while it may fix this path, something else might pop up somewhere else. But part of the over constraining is, if you look at this, this little bit of a tickle code that we have here, SDC is tickle based. Here we have a function. It's looking at, say, is this post route? What we're doing is we're inserting a constraint only for the benefit of the fitter. So if the fitter is not running, in other words, Timing Analyzer, if you open this up in Timing Analyzer will disregard this constraint and fall back to the normal crate clock constraint. So this way, you're over constraining inside the fitter. Timing Analyzer will look at your regular crate clock constraint and then accurately report if everything is passing timing or not. So this is a way to over constrain the. So I don't think that it's a bad idea to over constrain. Over constrain is a tool to use, not the only tool to use. And so consider that. And also consider that whenever you start focusing on a certain aspect of your design, other aspects of your design will have to provide a little bit of leeway in some form.
Sounds good. Before we get too far away from Design Space Explorer, maybe you want to go back to that now and show that off real quick before I give you some more questions.
Yes, thank you.
Sorry, I'm taking you all over the place.
No, it's good. All right, here we are. So Design Space Explorer. So here's the setup. I mentioned that you could do this over your network. And I said, I mentioned that you had to have stuff installed on the computers on your network to be able to accommodate something like that. This is the load sharing facility. One of the options you could do is secure shell as well. Once you've got all that set up, here are the different parameters to set that up to make it on your network. Now, you don't have to do it on your network. You think it's like, you know what, I'm good. You can just select local if you want, and you don't have to worry about all those. The exploration area. So we have different options here. We have different things that we'll be setting up inside here. So we'd select full compilation to be good. Then we go ahead and expand exploration points. You can go ahead and select single compilation if you want, but that's kind of defeats the purpose of running through Design Space Explorer. So you can go ahead and select Design Exploration. Now I talked about the different fitter settings that you can try. Here, what I have selected is seed sweep only. What that means is that I can go ahead and let's see, this is being, there we go. I can go ahead and select how many seeds I want in general. And what that'll do is the Design Space Explorer will run the fitter and input a different seed number every single time. So it'll be consecutive. Start at 1, go to 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth, just like that. And I mentioned also that one seed number isn't necessarily better than the other. It's very design specific. So that's the seed sweep aspect of it. Now, you can go ahead and do compilation strategies. You can say, it's like, I want, here's a compilation strategy that I would like. Go ahead and select all compilation strategies. What that means is that Design Space Explorer will do a compilation for this one, then this one, then this one, and so forth, all in the very first seed number. And then it'll increment the seed number, then do all the other compilation strategies, and so forth. And once you have everything like this set up that you want to, you can go ahead and make sure the design files are set up. Let's see, actually, there's nothing else I want to show there. This was the main area there. And then once everything is set up, let's see, where is, I am.
What are you missing?
I'm missing this. Oh, the start button. I was like,
Yeah.
where's the start button? It's right there.
I was like, it's right there.
It's right there. Thanks. Missing the start button. So once you have that all set up, you hit the start and go away for a long weekend. Memorial Day weekend is coming up, and you can have that thing run through all those different settings there. I've got it set up for all these different compilation settings. I think there's like 14 different settings there. 22 seeds. Yeah, I think my computer would still be working even after a long weekend. But that's how you get that set up. Pretty easy and straightforward, especially if you're not comfortable with command line scripting or anything like that. Design Space Explorer makes it easy for you.
Yeah. And just so like, yeah, the number of seeds that you set there, that's basically a multiplier. So it'll be all of those different options times the number of seeds that it's gonna sweep through. So that's gonna be a lot of compilations.
A lot. So it'll be, I think there's like 14 settings here. So it's 14 times 22. That's how many compilations is going to happen.
Yeah. All right. So we got more questions coming in. Question about Hyperflex. So obviously that's a large topic, but the question is basically, how can one take advantage of Hyperflex? Does removing resets help?
Oh, good question. Let's see. do I have? I think I've got some slides I can help illustrate hyperflex stuff. Let me bring my. I do talk a little bit about hyperflex in my trading class. Let's see. Slides didn't come up. Oh, here we go. This one. Okay. Okay, let's get. Okay, so about the hyperflex architecture. The hyperflex architecture, what it has a bunch of registers everywhere inside the routing infrastructure. The registers don't have to be used; they can be. Here we have an example of a hyperflex register as it exists inside the routing infrastructure. Here we have a MUX telling the FPGA whether it's going to be using the hyper register or not. And so, like I said, the hyper registers don't have to be used. The see, I know the question was specifically about resets.
So probably synchronous versus asynchronous, and removing resets or changing resets.
Yes. Okay. So the slides I have here doesn't have that inside there, but all right, I'll see this slide.
Have resets. I don't support them.
I'm sorry. What? Say the question again, please, or the statement.
I don't think the hyper registers support resets.
That's correct. Yes. So I was hoping to have something that would illustrate that, but you're correct. So the hyper registers are just simple D flip flops. There's no control signals inside there, so no clock enables, no resets at all. And so if you're starting a new design and you know you'll be targeting one of our hyperflex architectures, that would be either Stratix 10 or Agilex part. Again, starting a new design, if you want to fully utilize the hyper registers inside the part, don't code in clock enables and resets. You might say to yourselves, like,
Asynchronous
well, I have
resets.
well, yes, asynchronous resets. So there is a way to get around with the synchronous resets, and I particularly don't care for it. So I always advertise that just resets in general. With the synchronous resets, you can go ahead and the first hyperregister that gets used outside of the ALM can utilize the synchronous reset that was targeted for the ALM register. To get the full benefits, though, you have the hyper registers that don't have any control signals there. So with your design, things like, well, I have to have my resets. Like, well, yes, you do. To an extent, you'll want resets in areas of, and I do talk about that in my time enclosure class too. Let's see. There's, I think I'm going to be able to find it quickly enough here. So that there are areas in your design where you don't need resets on everything. You can get away with having resets in areas like state machines, resets in areas like feedback loops, resets on counters, of course, but you don't necessarily need resets in areas like a data path. A data path, what you want is a reset for a. So here I have talking about reset pulses here. What you want is to have a reset that would clear out the valid register, and then just have the valid signal follow along the data path there. So if you have a lot of data paths or data buses like that, you don't need resets on everything. And so again, when you're going into your design, if you're targeting a hyperflex architecture, look to see if you absolutely have to have resets inside there. And if you don't, then don't design them in.
So it's either it's minimizing what you're showing basically is minimizing the resets as much as possible.
Yes, minimizing resets as much as possible so that you can take advantage of the hyper registers. And with that being said, so talk about hyper registers. It's a pretty hefty topic in and of itself. With that being said, when you create your design, and you create your design with these registers that don't have clock enables and resets, that means the potential to use hyperregisters is there. It doesn't necessarily mean that those registers will go into hyperregisters. The tools will decide if those registers are good candidates for hyperregisters or not. And so what I'm getting at is there's no attribute you have to put on the signal there. There's no constraint. You don't have to do some type of special instantiation. The tools, when it's going through the timing portion of the routing and the retiming at that point, the tools will decide, like, you know what, to have a more balanced timing delay on this path in this clock domain, it makes sense that these registers get moved over into hyperregisters to create a more timing delay there.
Okay, so somewhat related question. If I were to add one from the chat, if I were to add one pipeline stage, is it enough to allow Cordis to add more registers for retiming? Or should I add a bunch of registers one after the other so the tool can move them around?
Let's see. So it did sound like an either or question. Could you read the first part of the question, Steve?
So I think the question is really asking, like, how many registers should I be adding to get the most benefit out of retiming? And I'm presuming in a HyperFlex device. They don't mention HyperFlex, but I presume
Okay.
how many registers, if it's just one or how many. And of course, you could probably go into how you would make that decision.
Yes, thank you. Okay. Okay, good question. So you can add a bunch of registers and the retimer could do it. Now, of course, when I say you can add a bunch of registers, you want to make sure that the latency of all paths affected have the same number of registers. So the valid signal going along with the data path, for example, you have other data dependency paths. You got to make sure that everything is balanced, because the tools will not check to make sure the functionality of your design remains the same. That's up to you to do. But with having said that, question is like, how many pipeline registers do I need to add? And what you could do is a fairly straightforward method is when you're looking at your design. So again, coming from my time enclosure class here, too many logic levels. So in other words, you're adding pipeline registers because you realize I've got too many logic levels. In this case here, we've got a depth of 16. We're failing timing. What do I do about that? The logic level is 16. What you could do is you look at what is it you're failing. So you could use this failing number, or what's the target period, and you go through. And here I've got the path. I've got the failing path, and I've got the interconnect and cell delays. Now, a straightforward way to do this, and since we want to be cautious, so that we can tackle the design once and I have to keep iterating over it. What I recommend to do is you look at the worst case interconnect. So the slowest interconnect delay that we have in the list here, and just scanning through this, looks like we've got 0.21 for interconnect. Then we grab a delay through a cell that is the longest as well. And scanning through here, looks like we've got 0.082. So 0.21 plus 0.082. Just give me a second here. Let's grab my calculator. Add those up. And so if we add up 0.21, 0.082, that gives us a number of 0.292. So now what I want to do is I want to divide 0.548, because that's the amount of time that I'm missing by. 0.548, divide that by 0.292, and that should actually give me the number of logic levels I need to reduce this by. And so here on my calculator, I got about 2. And so I mentioned here that you want to put in a healthy margin of 3. So 3 logic levels I need to reduce this by. So in other words, I need to reduce this from 16 down to 13 in order to meet timing. And in this case, what that means is in this particular path, I only need to add 1 pipeline register. If I add 1 pipeline register, assuming that it puts it right in the middle there, that means I have a depth of 8 on one side, a depth of 8 on the other side, and I would have satisfactorily reduced that the levels of logic in that path by 3 by splitting it up 8 and 8. So in this particular instance, I only need 1 pipeline register. So hopefully that made sense, the analysis that I went through there to figure out how many pipeline registers.
I think that's useful, Steve. I'm thinking the question is more talking about the idea of hyperpipelining, and maybe go into, briefly talk about fast forward compile, and using that to decide, oh, I only need to add one additional register in my path, or I need to to reach a certain performance level, I need to add multiple.
Right. Okay. So thanks, Steve. There's multiple ways to do this. If you're curious as to how many pipeline registers that you need to add, that would be the approach there. Fast Forward Compiler is a tool that works well. Also, what Fast Forward Compiler does is it speculatively changes your design. Okay, so it reads in the database, looks at it, it says, hey, you know what? You've got a bunch of registers with resets. I'm going to remove all these resets and see if I'm able to better utilize the hyperregisters. And so what Fast Forward Compiler does, it gets speculatively changes your design. These changes are not permanent. Speculatively changes your design, and it will give you a report saying, I removed resets on these registers, and the base Fmax was this, and your potential Fmax is now this. And then it will go through and it'll do that with clock enables. And it'll go through, it's like, you know what? Not only did I remove the resets and clock enables, but I also started adding pipeline registers on these areas in the clock domain. And when I added, 4 stages of pipeline registers, I got a potential Fmax of this. Now, the fast forward compiler will only work as hard up until it reaches the timing constraints in your design. So if you have a design and it's at 100 megahertz and your timing constraints is set for 300 megahertz, fast forward compiler will pull out. It will use its bag of tricks. It'll start doing these things until it runs out of its tricks, or until it reaches the Fmax. So fast forward compiler is another tool that will easily tell you the paths that require change in order to reach a potential Fmax. Again, it's up to you to maintain the functionality of your design. Fast Forward Compiler has no idea about the functionality of your design. It'll just start doing stuff that it knows to do to to create a good Fmax.
Right. Let's switch gears a little bit. What is the recommended way to constrain a clock crossing FIFO?
Oh, good. All right. So I'm gonna take this in 2 parts here. The one part I do talk about CDC constraints. Oh, let's see, that's in my hang on a second. Here, I promise. Pick that in 2 phases to just talk about clock domain crossing in general, and then yes, here it is. Okay, clock domain crossing in general. So here we have a synchronization chain. Just go back to my synchronization chain right here. We see that R1 is on clock A domain. Rs 2, 3, and 4 are on clock B domain. The here we want to do some QSF settings that we have. We have synchronizer identification.
Sorry, Steve. You want to go full screen?
Oh, yes, I do. Yeah, full screen. Yes, thank you. And my laser pointer. All right. So here we have synchronizer identification, forced if asynchronous. So in other words, what we're telling the tools is, and the tools can automatically detect asynchronizer. For some reason, sometimes the tools do not. I wouldn't necessarily call it a bug. I would just point more to my ignorance of how the tools determine what a synchronizer is. But you can go ahead and tell it if you don't want to leave anything to chance. Synchronizer identification, forced if asynchronous. So in other words, if it's going to be, if the clocks are asynchronous between those two, forced if asynchronous, and if that's the case, so if we do have 2 different clock domains there, starting at R2, you're telling tools, that is my synchronizer chain. So I'm crossing from one clock domain to another clock domain. When you do that, you want to have a synchronizer chain. Here, we have a global assignment, and this is the default. This is the default setting. If you were to open up the Quartus defaults file, you would see this assignment in there, and it would have a number of 3. So I put this in there for information purposes only. You could also put this inside of your QSF file, and you could change that number to whatever you want. 3 is a good number. 3. It should. I wouldn't expect it to be over 3. 2 is also a good number. 3 is a good number. But anyway, that's the default setting. But you could also, instead of having it as a global assignment, you can have it as a local assignment. If you say, like, you know what, I've got an exception here to what I want it more localized. I just kept it at 3, but you could change this to any number you want. So here we have an instance assignment. So I'm targeting a specific instance in the design. It's not going to be for my entire project. I'm just targeting an instance, and here's R2. I'm going to say synchronization registered chain length is 3. So I'm telling the tools I have a synchronizer, and the length of it's going to be 3, and that's what I've got there. So for the SDC constraints, I just have my create clock constraints in there just for completeness there. Set a false path. I don't want the tools to analyze the path between R1 and R2. So this is completely cut from timing analysis. Now, when you do that, the tools will be basically say, it's like, oh, okay, so you don't want anything, there's no timing here. That means I can place R2 as far away from R1 as possible because there's no timing. That's not what you want. You do want to cut that path, but there's a couple more constraints that you want inside there. Okay, false path. You could also do the set clock groups. Now, the difference between the set clock groups and the set false paths is that set false paths goes from, it's unidirectional. So it goes from, in this case, R1 to R2. They'll cut that path. Now, if there's communication going from R2 to R1, it would not cut that path. But the set clock groups, that's what that would do. Set clock groups would cut the path going from A to B and from B to A. So set clock groups goes in both directions. Set false path is just one direction. If you want it both directions, then you have to put another set false path command inside there. Now what you want to do is you want to, if this is a bus, R1 to R2, if this is a bus, so if it's not a single bit, if it's a bus, you want to say, it's like, you know what, there has to be a certain amount of skew that I can tolerate between the two. So in other words, bit 1 can only be skewed by a certain number of nanoseconds from bit 2 or from all the other bits, for example. And that's what we're doing there. We're setting the max skew right there, going from R1 to R2, get the skew value from the clock period, source clock period. So what we're doing is the skew that I can tolerate, I'm going to use the source clock as reference. I got to have a multiplier of 8. So the source clock period in this case was 10 nanoseconds. What I'm saying now here is that the skew that I can tolerate between the bits of the bus here is 8 nanoseconds. I cannot tolerate any more than 8 nanosecond skew. So now we've got the skew involved here. So in other words, R2 could still be placed as far away from R1 as possible, but now all the bits of the bus have to be placed within 8 nanoseconds of each other. So we're not quite done yet. Now we can go ahead and set a net delay. So net delay is based solely on the net, not based off the clock pins. We do a net delay, and in this net delay, we do a we get the value from clock period, destination clock period. So we're just going to say, is like, you know what, we're going to use the destination clock, 15 nanoseconds, as a source. I'm going to have a multiplier of 0.8. So this case here, the net delay from R1 to R2 will be 12 nanoseconds. And so now I've constrained the design. There's a false path between the two, so there's no relationship between clock A and clock B, but I've constrained the design because I do want data to come over here in a certain amount of time, and this is the time that I've specified there. Then I have my synchronizer chain to mitigate any metastability problems that come up. Okay, so that's the clock domain crossing. So having explained that, let me go ahead and pull up. I did find information about the DC5 pull constraint, DC5 for viewer to constrain it. And so this question comes up from time to time. So I actually came prepared for this just in case it would come up. I just did a search, did a Google search Intel FPGA, constraining dual clock FIFO, and this article came up, and it's really helpful. And it basically goes through the same constraints that I had listed in my time enclosure class there. So here we have we have a max skew, we've got the net delays, and the max skew and net delays talk about the source clocks and the destination clocks as well. So you constrain it in a very similar way that you would with just a regular synchronizer. Okay, hopefully I addressed that question satisfactorily too.
Sounds good. Question in the chat, kind of related to both the topics we've just been talking about. One user is saying that a technique they've used to resolve timing issues is to insert multiple FIFOs between two functional modules, say A and B. And so A and B can be put into two separate positions that may be further apart from each other in the device. This is only useful for those latency insensitive applications. Going back to Hyperflex sounds similar to this. What are the pros and cons of adding FIFOs compared to Hyperflex? Right off the bat, I'd say it's kind of basically the same idea.
It is, yeah, it is the same idea. So the pros and cons. So the cons, with the FIFO, you have more circuitry involved with the FIFO, but maybe you need all of that, and that would be fine too. So inserting multiple FIFOs there, especially if you're using dual clock FIFOs, that helps, bridges the clock domains itself. But if you have a with the Hyperflex registers, you could do the exact same thing. And in fact, there is you could do a set faults path. I don't have this slide up right now, but with the SCC commands, you could do a set faults path. You could put what is it? It's latency insensitive, or I think that's a switch. And if you do latency insensitive, that tells the tools like, hey, you know what? We can retime between these clock domains. We could add pipeline registers between these clock domains because the designer doesn't care about the latency between these clock domains. It will insert pipeline registers. So the only con I can think of is, like I said, the FIFO just has more circuitry. Otherwise, you've got the pretty much the same idea.
Yeah, the Hyperflex registers are basically like a FIFO, and registers of the FIFO may if you create it yourself might get implemented in Hyperflex registers, right?
Right.
Yeah.
So yeah, it sounds like a very similar approach as what you would do with the Stratix 10 or Agilex.
Okay. So we're almost running out of time. So get those questions in. Let me see what else we can do here. Let's see. Oh, I think you already answered this one. Now let me skip that. Oh, this is interesting. Oh, is there a question on the phone? I heard somebody unmute. Oh, okay. So what is the best way to physically see a path? And I'm not sure if that's talking about like the chip planner or what, Steve. So you can take that.
Okay. It did. Yep. when I did my Design Space Explorer question, I did have Quartus open. That is gone. Let's see. I think I've got. Let me escape out of presentation mode of this one. You can physically see a path, and I remember I actually talk about that in this here too. And Bob. Not. Okay, no, it wasn't in this presentation that I had. The now I can't remember what class is it, but okay. So anyway, so if you're in Time Analyzer, you have a Feeling constraint. You can cross probe to that Feeling constraint. In fact, now that I'm talking about this, I can go ahead. There's another section of class that talks about that. Let's see, that was in. Sorry, give me a moment here. There we go. So here, what I did is when you're in Time Analyzer, you could actually go ahead and do a right click on your failing path and cross probe. You could locate that path. That's what I have here in this screenshot here. Locate path in, what I did in this case was Technology Map Viewer. So Technology Map Viewer, it showed me the path that is there, and I can see all the cells that were involved in the failing timing path that I have here. Now, not only can you cross probe it into the technology map viewer, as I've showed here, but you can also cross probe into Chip Planner. Once inside a Chip Planner, you can overlay the timing values on that particular path. Doing it inside a Chip Planner has the benefit of you can see where that path is going. You can also cross probe. You can also cross probe entire modules, and I know I do have that screenshot here. You can cross probe. There we go. You can cross probe entire modules to see where they're located. So if you have the path already cross probed inside a Chip Planner, you could also cross probe module. That's what I did, is I cross probe from Quartus into Chip Planner. And so here in this particular design, I have instance 4 and instance 35 color coded inside there. And if I had the path, if I have the path or the module, you can see where the modules are. And that can aid you in doing what's called a logic lock region inside a Chip Planner. Logic lock region, what you do at that point is you are telling the tools that, hey, this module that I have here, you kind of place far apart, I really need a little bit closer. So you're constraining the tools into where it can place the particular module, which means that there's going to be a give and take. I'd say by and large, the tools do a very good job as far as placing routing goes. Sometimes it doesn't get quite right. Sometimes it needs a nudge from us. Just saying all of that, so when you do place a logic lock module there, just try to place a module a little bit closer to wherever it's communicating, that there's going to be some consequences as a result. And what happens, hopefully, isn't terrible, but there could be some other timing closure issues that crop up as a result.
Okay. So we're almost out of time here, Seth. Just a couple of things. I just put a survey link in the chat. And also, Steve, there was a request if you could go back to the main presentation and put up
Yes.
the resources slide again, so that gets into the recording, so that people can see the resources that you recommend. And that's also somebody asking about the timing closure class. So that's our timing closure class that folks can register for. But let me see, is there any other questions we can hit real quick here? Let's see. Okay. General question. There's so much, and maybe you have like 1 minute to answer this, Steve. So there's so much that determines successful timing results. What do you do when you're at what stage of the design? Potentially a long answer, but even a basic idea would be good. I think, Steve, what you should do with that is basically say, what you should focus on in each stage of the design very briefly for timing closure.
Yeah, in fact, this would be a plug for the timing closure class. So some of these slides that you saw there, I pulled from my timing closure class. But briefly, it'd be about baselining your design. And baselining your design is making sure you have good architectural techniques for the technology that you're targeting. And baselining your design includes not only good HDL coding practices, but good timing constraint coding practices as well. I go through another phase in that class called analyze, and analyze would be becoming aware of the various reports that exist inside of Quartus to help narrow down and tackle a particular timing closure issue that you're after. There's a lot of excellent reports inside of Quartus and Timing Analyzer to help you with this. So it's good to have an understanding of what those reports are telling you. And then on top of the third section of my timing closure class is improve. So once you've analyzed the reports, once you've narrowed it down, go back to improve your design. Maybe some things that you forgot or left out during baselining. So briefly, those are the three main stages that I talk about in my timing closure class. That's what I'd recommend. Of course, the devil's in the details with something like that. But in the timing closure class, we do go into more details about those methods.
That was a fantastic 1 minute answer on that, Steve. if I may say so myself, that was great. You got it all. All right, I think we are out of time, so you want to go to the final slides, and we'll put this up for a little bit here, so it'll be in the video, and then go on to the final slides, and so we can stop the recording.
All right, and thank you everyone for attending. Thank you for the questions. And hope to see you in a future class that I teach. And that is all.
And just go back to the survey link I put in the chat. I will put it in one more time in case folks missed it. and we greatly appreciate it if you would fill out that survey. So I'm stopping the recording now.
All right. Thanks, everyone.